Okay, so in today's class, what we'll do is that first just have a look at what we did last time and then start with a new topic. So, in the last class, basically we started module 5, which was on nonlinear dielectrics. Now, these are the materials which are different from linear dielectrics in the sense that the behavior of dielectric constant of polarization as a function of electric field is not linear, and they show some extraordinary properties like coupling of electrical and mechanical parameters. So, such as what you see in piezoelectric materials, effect of temperature on polarization, such as in pyroelectric materials, and then you have when you switch when you have a polarization electric field hysteresis loop, which happens in ferroelectric materials. And the basis for these materials is the crystallographic basis. So, out of all the point groups, your 20 are non-centrosymmetric, actually 21 are non-centrosymmetric, and out of 21, except 432, 20 non-centrosymmetric point groups are all piezoelectric. So, the requirement for piezoelectricity is that the material should be non-centrosymmetric in nature. And then out of these 20, 10 are pyroelectric, which are polar. So, not only they are non-centrosymmetric, they also have a unique polar axis, along which the properties are different at the ends of the polar axis. And then out of these 10, a few are ferroelectric, in which the direction of polarization along the polar axis can be reversed by reversing the direction of electric field. So, additional constraint imposed on the pyroelectric materials makes them ferroelectric. Naturally, all the ferroelectric materials are pyroelectric and piezoelectric, but vice versa is not true. So, what we will do in this lecture is we will take our discussion forward with the discussion on ferroelectric ceramics. Now, among all these three classes of materials, ferroelectrics have generated a lot of interest simply because they are extraordinary. They are ferroelectric, they are piezoelectric and pyroelectric at the same time. So, that naturally makes them interesting, and the effect ferroelectricity so effect of ferroelectricity or ferroelectric effect was observed in 1921, and this was observed by a Czech scientist, Roger Walasek, and he looked at what is called as Rochelle salt, whose formula is KNaC4H4O6.4H2O. So, he was the first scientist to discover ferroelectricity in Rochelle salt, and this at that time did not generate enough excitement because of a variety of reasons. And however, later on, after the Second World War, the research on just about the Second World War, there was a renewed technological interest in these materials, and that could have been because of a variety of defense and military applications, and later the other applications also came into picture. Now, as a result, in subsequent years, variety of materials were discovered, and among them ferroelectric materials that were discovered later on after the discovery by Walasek is for instance, you can have triglycine sulfates and similar compounds. You can have potassium dihydrogen phosphate and again similar compounds, isomorphous. Isomorphous will mean isomorphous means same structure. So, isomorphous compounds, and you can also have materials like ferroelectric sulfates. Plenty of sulfates are there in the literature which have been discovered, and then you have of course Rochelle salt, which was discovered earlier, and compounds similar to Rochelle salt. And then you have titanates or perovskites, and here the examples are barium titanate, lead titanate, and similar compounds like potassium niobates, etc. So, basically titanates or perovskite structure compounds. So, of course, potassium niobate is not a titanate, but it is a perovskite structured compound. And then you have complex oxides, and this would mean your materials like strontium bismuth tantalate, bismuth titanate, which are Orivillus family compounds. So, variety of these compounds were discovered. Rochelle salt discovery was made at lower temperatures. It was ferroelectric at lower temperatures, but there are many more materials which are ferroelectric at room temperature, and that is what is exciting from the technological point of view. One of the important requirements for a ferroelectric material is that it should have a transition temperature, which means above a certain transition temperature. So, this ferroelectric effect is associated with what is called as Tc, which is called as a Curie temperature. Curie temperature, and what happens is that, so you have above Tc no ferroelectricity, and below Tc ferroelectric effect is observed. So, this transition temperature is quite important. We will come to the derivation of this Curie's law in a while, but this transition temperature is important because the magnitude of this temperature makes the material useful for technological applications. So, for as you can imagine, for most of the technological applications, this Tc has to be larger than room temperature, in fact as high as possible. For instance, if you go for high temperature sensors, etc., this Tc better it is if it is higher. So, from that point of view, higher Tc is better. Now, what we will do is that although there are a variety of compounds which have been discovered, most of the discussion on ferroelectrics we will restrict to titanates, which are the most studied and simplest of these compounds, in order to explain the ferroelectric phenomena in variety of materials. So, we will start first with the concept of, in ferroelectric material, given that these ferroelectric materials have what you call as, this is the ferroelectric effect as we discussed last time. So, this is polarization, this is electric field. Polarization is nothing but charge stored. So, these two states which are equal and opposite, called as plus PR and minus PR. PR is remanent polarization, and these two states tell you that there is a finite magnetic finite dipole moment at temperatures lower than Tc in the absence of any electric field, which means material can have either plus PR state or minus PR state at zero field, and this is what makes them exciting for variety of applications. So, we will start with the concept of permanent dipole moment. So, typically what you have is a centrosymmetric material. So, a centrosymmetric material, because of symmetry, will not show any polarization. So, for instance, you take example of a cubic material, or now let us say we take this form of cubic barium titanate. Okay. So, this is barium titanate cubic, right. Now, what we do is that we label the atoms here. So, you have oxygen sitting here on the faces of this cube, and you have barium going here, and as you can understand, titanium goes here in the center of the unit cell. So, this is barium, this is oxygen, and this is titanium. Now, since this material is centrosymmetric in nature, which means it does have a center of symmetry. So, if you look around this point, all the other positions are symmetric around this point. For instance, these two positions above and below, or on the sides, all of them are equivalent position. So, as a result, this material does not show any dipole moment. So, net dipole moment for this is equal to 0 because of symmetry considerations. Now, when the material becomes non-centrosymmetric, so now if I draw a non-centrosymmetric state, the material becomes tetragonal. So, BaTiO3 non-centrosymmetric and this will happen at temperature T less than Tc. In the previous case it was T greater than Tc, and it would, in this case it would happen at T less than Tc. Now, in this case of course, and this happens when the material is tetragonal, and in the tetragonal form what will happen is A is equal to B is not equal to C, and alpha, beta, gamma remain equal to 90 degrees. So, if I draw the unit cell now, and if I just now put the atoms, so you have barium atom sitting here, and the oxygen atom, let me see what the color that we used last time, red. So, oxygen goes at the centers here, this is oxygen, and the titanium goes in the middle. Now, what happens in this situation is, in the ferroelectric state, what happens is that this titanium atom does not sit at the center of the unit cell, rather where it sits is, because if it was sitting in the even for this structure, if it was sitting right in the middle of the unit cell, it will not give rise to any dipole moment, again because of symmetry. Now, for the ferroelectricity to occur, this atom which is at the center of the unit cell will shift either up or down. So, what you will have eventually is either a position which is stable here or a position which is stable here, and this is the center. So, this is, let us say, plus a state, this is a minus a state. So, what happens here is, now the center of, now what is the negative charge here? Negative charge is oxygen. So, you have oxygen octahedra. So, this is oxygen octahedra. So, this is oxygen octahedra. Now, if the titanium atom was sitting at the center of this octahedra, then centers of positive negative charges would match and there will be no net dipole moment. However, when this titanium atom is shifted slightly towards top or towards the bottom, which is along this axis, which is 0 0 1 direction. So, it is shifted either along 0 0 1 direction or 0 0 bar 1 direction by a little margin, then it gives rise to what is called as a finite dipole moment. So, this gives rise to finite dipole moment in the absence of electric field. So, it is polar in that sense, and there is strong energy requirement for this. Now, this configuration is favored for this particular kind of material, because free energy, as you know, free energy is G is equal to H minus Ts, and this change in free energy determines, for a system to be in equilibrium or to be in the stable state, the delta G of that system must be negative. Now, what happens is that when the titanium atom is shifted in either positive z direction or minus z direction, the free energy of this crystal is at a minimum as compared to when it would be at the center. So, there is a strong energetics behind it, and this plus state is characterized by what we call as plus PR state, and this minus state is characterized by what we call as minus PR state at 0 field. Remember, this is at 0 field. So, finite dipole moment at E is equal to 0, and this is characterized by these two states. So, when you have this kind of material subjected, so now when you draw polarization versus hysteresis plot, so if you draw such a plot for a centrosymmetric state, which means it is in a cubic state, then the material shows this kind of behavior. So, this is for a at T greater than Tc. When you draw the same plot for this barium titanate at lower temperatures, then the plot is something like so. These two, this is minus PR, this is plus PR. So, visually it is looking as if it is unequal, but it is so basically what will happen is, if I just remove this line, make this line a little in the middle, right, and remove this line as well and take this line through the middle. Okay. So, this red would be the centrosymmetric, and this would be for non-centrosymmetric barium titanate. And on the x axis, and this will be called as saturation polarization plus CPS, this would be called as minus PS, and the zero polarization fields are called as coercive fields. So, this is plus EC and this is minus EC. So, this is how it would be looking when you switch a material in the polar state, polar non-centrosymmetric state, and in the centrosymmetric state. Now, this has strong implications in the terms of energy. So, how it looks in terms of energy? Now, when you draw the free energy of such a crystal, so I am just going to do a little qualitatively here, because quantitatively we will do somewhat later. So, if you draw a position, or it could also be polarization, and then this is energy, free energy. So, if you draw the free energy of such a crystal, now at T greater than Tc, so let us say this is the position x is equal to 0. So, x is equal to 0 would correspond to center of unit cell along 0 0 1 axis. Okay. So, this is let us say z is equal to 0, or I say z is equal to 0, that is more appropriate. So, in the non-cubic state, in the centrosymmetric state, sorry, the material will show this kind of. So, free energy minima occurs at z is equal to 0. So, this is for cubic state. But what happens at temperatures lower than Tc? This free energy minima behaves like this. So, you have two identical states, plus z minus z, and this is corresponding to plus PR, this corresponds to minus PR, and this is at so, you have states which are two stable states which are energetically equivalent. So, these two energies are of course equal. So, depending upon how you go in the cycle, it will either be at minus z or plus z, and they would correspond to this situation. So, basically what it would mean is that if you correspond to the structure, if you go back to the structure in the previous slide, in this slide, So, this state will correspond to basically right side minima, and this will correspond to the left side minima. So, right side minima and this would be left side minima. All right. And when you now this is the situation at E is equal to 0. When you start making E finite, which means when you start applying the electric field, then what will happen is, depending upon the direction of electric field, these wells will start tilting, and as a result of tilt, the atoms will move from one side to another, because as you can see that either the atom is stable here or here, but not at the same time in both places. So, it either goes from this to this position or from this to this position, depending upon the direction of applied field, and that we will see in a little while. So, what will happen? So, when you draw the hysteresis loop, let us say we draw the hysteresis loop here. Okay. So, I know what the situation at these points is. At these points, it is looking something like this. Okay. So, let us say this is the minus PR state. So, this is minus PR, your atom is sitting on this side, and this is your plus PR state. So, here, so these two are equivalent position, your atom is sitting on this side. Okay. Now, what will happen when you start applying field? Now, of course, when you go in this direction of field, then by the time you reach there, this must have gone from this position to that position, which means as you go up, for instance, at some position here, the scenario would be, you would have a scenario like this. So, your atom is still sitting here, but the energy wells are slightly tilted to the other side. So, as a result, it is getting slowly the momentum to move to right side. Now, when it reaches there, then situation is like this. So, it goes completely to this side, and when you go back here, then the wells, then you reverse the direction of applied field. So, wells again start tilting in the opposite direction. So, as a result, it goes in this position. Now, for instance, in this position, what will happen is that you will have now the wells will start tilting in the opposite direction. So, what you will have a scenario like this. So, your atom is still sitting here, and when you come back here, again there is no well as such there, the wells are too much tilted. So, they completely favor this direction. So, this is how it is going to look like when you switch the material from as a function of electric field. So, this of course is polarization, and this of course is electric field. So, these potential wells, they shift, they tilt as you change the direction of applied electric field, determining the position of the atom on either side of the well. Okay. And so, this is what energetically it is going to look like. It is a very qualitative description. We will look at the quantitative nature in a little while when we solve the when we go into Landau theory, but this is how qualitatively energetics of a ferroelectric material is going to look like. So, I hope that you understand what we mean here. Essentially, what it means is that a ferroelectric material is a material which is non-centrosymmetric, which is polar, but at 0 field it has two equivalent minimas, and the center titanium atom, for instance, in the case of barium titanate, sits in either one of these positions, depending upon how you have arrived by switching the electric field. So, and these two positions, because at minus PR it has to sit in, let us say, in this well, at plus PR it has to sit in this well. When you go from plus PR to minus PR, it has to move from right to left or left to right. So, how would that happen? That would happen like this. So, if you were sitting, let us say, on the left in this position, and when you start applying the field in the positive direction, the wells will start shifting. So, the wells on the positive side get more deeper, and on the negative side they get little higher. So, as a result, you are developing a direction of movement from this to that, but there is still a minima there. So, the atom sits here. Now, you reach a state when you completely change the field, so that this would be completely sitting in the right side well, because the left side well minima is apparently lost. And when you again make the field back to 0, then both the wells become equal, but this atom still sits there because it has a large barrier to overcome. And when you start switching back in the reverse direction, again the wells on the left start getting deeper and wells on the right start getting shallower, but not until when you reach minus ps state. That is when the wells on the right become completely flat, so that the atom jumps over to the side on the right. So, and this happens actually at this point. So, which is minus EC and plus EC. So, at minus EC, the atoms from the right well will jump into the left well, and this would be this would completely get stabilized when you reach minus ps state. Similarly, atoms from the left would jump into right at plus EC, and crossover would happen at plus EC, and they would be in an extremely stable state at plus ps direction. So, this is what energetics means of these ferroelectric materials. Another thing is as I said, that these ferroelectric materials show a transition, which is ferroelectric transition, and this ferroelectric transition occurs at a temperature Tc, and this is often called as Curie transition, which means, and which also means is that these ferroelectric materials follow what is called as Curie-Weiss law. And this Curie-Weiss law is expressed as, so the susceptibility of the material you can express as 3 Tc divided by T minus Tc, where Tc is the transition temperature. And what it means is that they are these materials are ferroelectric at temperatures lower than Tc. At temperatures above Tc, they become non-ferroelectric or paraelectric in nature, losing all the permanent dipole moment. So, what we will do is that now in the subsequent part of the lecture, we will we will determine basically how this expression comes up. So, basically derivation of Curie's law, and this Tc, for instance, is about 120 degree centigrade for barium titanate, and for about 450 degree centigrade for lead titanate. So, these are all useful materials because Tc is higher than room temperature. So, basically below 120 degree centigrade barium titanate is in ferroelectric state, and at temperatures above 120 degree centigrade barium titanate would be in paraelectric or non-ferroelectric state, giving rise to zero polarization. And basically what it would mean is that it would mean either, so at T greater than Tc, material is in paraelectric state. Now, this would have two meaning. One meaning is either the material has gone into centrosymmetric state. So, centrosymmetric state, centrosymmetric means no polarization at all in any case, or what it would mean is that it has gone into a non-centrosymmetric state, but a state where all the dipole moments are randomly distributed with respect to each other, which means thermal forces have taken over and they have put or the thermal forces have taken over, randomizing all the dipoles, giving rise to zero polarization. So, it would mean any of these two scenarios, but in the end what it would mean is zero dipole moment. So, now what we will do is that we will look at the proof of the Curie-Weiss law, and then we will switch on to the next topic. Okay. Now, we can say that in a ferroelectric material, this we have not yet gone into the complete intricacies of ferroelectric materials. What basically it means is that given that each of these unit cell, so this is the barium titanate unit cell, so all of them have a let us say each cell has PR in this direction. Now, what it has meant in the terms of ferroelectricity is that in all across the material, when you reach the very high field, all of these dipole moments align in the direction in the direction of light field, and they give rise to maximum possible polarization. But even in the zero field state for a ferroelectric material, some of them have left oriented. Now, how it looks like, we will look at that in a little while, maybe in the next lecture or so. But what it means is that there is some spontaneous alignment of dipoles which is left over when you reverse the field to zero field. So, some, you can say, spontaneous alignment of dipoles at t less than Tc, even when E is equal to 0, and this is what gives rise to plus PR. So, there is some sort of interaction which is taking place between the dipoles, and this happens. This we will also see in case of ferromagnetic material. So, basically you have one dipole vector here, but there are some other neighboring dipole vectors which are all aligned in one direction, and this is a state which is how should this state be created? There should be something behind this state, and this happens due to what we call as a local field. So, this theory of polarization for ferroelectrics is also called as local field theory, and this basically what it says is that this local field is in the direction of dipoles, or dipole align themselves in the direction of this local field, giving rise to a spontaneous polarization in the material, spontaneous or remnant polarization in the material. Now, this phenomena happens at temperatures which are lower than so this happens at T lower than Tc, and this means that the thermal energy kT is insufficient to randomize these dipoles. So, these are the dipoles. So, if kT is smaller than the local field, then they stay together, but if kT is larger than E prime, then they randomize, and this is what happens at T greater than Tc. If the material was still in non-centrosymmetric state, which means it was still polar, each crystal still has dipole moment, but those dipole moments are unable to hold themselves together in the aligned state. They become randomized simply because thermal energy is much larger than that local field. So, this is one theory which is given for ferroelectrics, that at temperatures greater than Tc, the thermal effects take over, randomizing the dipoles, but at temperatures lower than Tc, the local field is, or the energy which is created due to local field is larger to hold these dipoles aligned in one direction, giving rise to what is called as spontaneous or remnant polarization. So, thermal effects are much less dominant at T less than Tc. So, now looking back what we did in module 4, in module 4 we discussed polarization. What was polarization equal to? Polarization was equal to chi into epsilon naught E, and what was chi? Chi was epsilon r prime minus 1 into epsilon naught E. Now, this is the macroscopic term. So, of course, we have taken what is called as macroscopic field here. Now, what it means microscopically is n alpha E prime, and this E prime is local field, because now here we are looking at microscopic quantities, because alpha is polarizability and polarizability is microscopic property. So, this local field E prime, its magnitude as we discussed in the module 4 was equal to E plus P divided by 3 epsilon naught. So, I will just leave a link here, module 4, in the beginning of module 4, right in the beginning of module 4, maybe in the first or second lecture. So, if you go back to module 4, you will find this expression for E prime is equal to E plus P divided by 3 epsilon naught, and here alpha, as you know, is polarizability, epsilon r prime is nothing but relative dielectric constant, and epsilon naught is the permittivity of free space. So, what you do is that now you substitute this E prime into this expression. So, what you get here is P is equal to n alpha into E plus P divided by 3 epsilon naught, and this is equal to n alpha E plus n alpha P divided by 3 epsilon naught, and this is equal to. So, what I am going to do is that I am going to shift this term to the left side. So, P, so I am taking this here. So, this becomes P into 1 minus n alpha divided by 3 epsilon naught, and this is equal to n alpha E. This P becomes equal to n alpha E divided by 1 minus n alpha divided by 3 epsilon naught. Okay. Now, we know that chi is equal to epsilon r prime minus 1, chi is the susceptibility, and this is equal to P divided by epsilon naught E. So, chi will be equal to epsilon r, oops, scales have shifted, let us bring them back, epsilon r prime minus 1, this is equal to n alpha E divided by 1 minus n alpha divided by 3 epsilon naught into epsilon naught E. So, of course, you cancel E's, and what this becomes equal to is, so chi becomes equal to n alpha divided by epsilon naught divided by 1 minus n alpha divided by 3 epsilon naught. So, so what it basically shows is that when n alpha by 3 epsilon naught approaches 1, then this denominator will be approaching 0, and when the denominator approaches 0, the chi becomes infinity, and that is what is for ferroelectric materials, because ferroelectric materials have very large response to the applied field. So, which means they show very large susceptibilities, and what this makes sense. So, what basically it makes is, so this would mean chi tending to infinity, and this is what makes sense, because at t, so near the T c, this is true, because when you switch the ferroelectric material and when you plot the dielectric constant versus temperature, they show this kind of behavior, and these are extremely large susceptibilities, very large susceptibilities. So, this plot basically suggests that at temperatures near T c, and T c is somewhere here, so this is T c. So, in this region near T c, material shows very large susceptibility as well as dielectric constant, because epsilon r prime is nothing but related to chi plus 1. So, what basically it means is that this n alpha, as it approaches n alpha by 3 epsilon naught, as it approaches 1, and this happens near temperatures T is equal to T c, chi tends to be infinity, and this is what represents a ferroelectric behavior near T c. So, this makes kind of sense, and at this point, given that epsilon r prime and chi is extremely large, you can ignore the contributions from, so ignore the contributions of alpha electronic and alpha ionic, given that these are going to be very small contributions in any sense. So, as a result, you know that net alpha is equal to alpha electronic plus alpha I plus alpha dipolar. So, I am going to neglect these. So, let us say alpha is equal to alpha d at least at temperatures which are closer to T c, because susceptibilities are very large. So, as a result, I can write this. So, let us say I define here alpha is equal to alpha d by c is equal to c divided by k t, and the c is called as Curie constant. Okay. So, now this is kind of relation that we have similar relation we have seen in when we did module 4, when we analyzed what is called as dipolar polarization. So, it is not very different from what we are doing now, but nevertheless it is a completely different exercise altogether. So, the previous expression was, so chi was equal to n alpha divided by epsilon naught divided by 1 minus n alpha divided by 3 epsilon naught. So, here what I am saying is that I will make this alpha to be equal to c by kt. So, when I make the replacement, so let us say n alpha, first of all let us look at n alpha itself, n alpha divided by 3 epsilon naught, and this becomes n divided by 3 epsilon naught into c by kt at t closer to Tc, n alpha divided by 3 epsilon naught is equal to n 3 epsilon naught c divided by k T c, and this is nothing but equal to 1, okay, as we have seen earlier. So, if this is true, then T c is equal to n c divided by 3 k epsilon naught. So, what you do is that you take the T c there. So, this becomes n c divided by 3 k epsilon naught. So, this T c is called as Curie temperature. Okay. Or let us say, instead of writing this here, you just write it as that T closer to transition, that is more appropriate, because when you talk about transition, then you define transition temperature as T c. Okay. So, now below this, now what happens below T c? Now, below T c, of course, you have this alignment of dipoles which take place. As a result, you have this spontaneous alignment of dipoles, spontaneous polarization. So, below T c, you can define the C to be equal to alpha naught into k T, and this alpha d into k T, let us say. Let's just make a distinction between the high temperature temperatures. So, let us say alpha naught, some polarizability, of course, it is higher than electronic ionic in any case. So, you write this T c to be equal to, now T c was equal to n c divided by 3 k epsilon naught, and what it becomes equal to is that n into alpha naught k T divided by 3 k epsilon naught, k cancel each other, and what you get is n alpha naught T divided by 3 epsilon naught. So, that means T c by T become n alpha divided by 3 epsilon naught. So, this is an important expression which you get as a result of approximations near T is equal to T c, and this now when you substitute back. So, your chi was equal to n alpha divided by epsilon naught divided by 1 minus n alpha 3 epsilon naught. So, in the previous slide we have n alpha divided by 3 epsilon naught is equal to T c by T. So, this would become 3 T c by T, and this would become 1 minus T c by T, and if you take T in the, if you cancel the T's here in the denominators of T c by T, then this becomes 3 T c divided by T minus T c, and this is what is called as Curie-Weiss behavior. Curie-Weiss law. And what it means in terms in graphically is that when you plot let us say dielectric constant or susceptibility as a function of temperature, then they increase little slowly in the beginning, but they reach very high values at some temperature and then they start falling. So, this is your Tc. Material in this part will be ferroelectric state, and here it becomes paraelectric in the paraelectric state. And this is a very important outcome, because this gives you not only magnitude of a temperature which is called as Curie's temperature, but also the behavior of material near Tc and below and above Tc. So, what happens in ferroelectric state is dipole moments, they align with respect to each other. So, which means the thermal energy kT is less dominant, thereby not interrupting the spontaneous alignment of the dipoles. In the paraelectric state, you have randomization of dipoles, and here thermal energy is large enough to make this distribution of dipoles random. As a result, you have P which is not equal to 0 at E is equal to 0, but here P is equal to 0 at E is equal to 0. So, as a result, material behaves like as if it was a linear dielectric in the paraelectric state, and it behaves like a ferroelectric or nonlinear dielectric at temperatures lower than Tc. So, this is an extremely important exercise from the point of view of behavior of materials. I will find out some values and just to give you some of the Tc's of some materials, candidate materials. Let me just look at some of my notes. Okay. So, for instance, Rochelle salt, it has a Curie temperature of in degree centigrade, sorry, Curie constant, not Curie temperature. This should be, so the value of C, and then, or let us say let us just write value of Tc, let us not worry about C, and then polarization, and then epsilon r at Tc. So, Rochelle salt shows a Tc of around 24 centigrade, 24 degree centigrade. That is why Wolfsek could observe in Czech Republic at 24 degree centigrade, because if he was in India, he would not be able to discover ferroelectric effect, because in India and some other temperatures higher than 24 degree centigrade, he has to be here in winter to observe ferroelectricity in Rochelle salt. But in Czech Republic, 24 degree centigrade is the temperature which is considered as high temperature. So, as a result, he could discover the ferroelectricity. So, 24 degree centigrade is the transition temperature. Polarization in microcoulomb per centimeter square is about 0.25, not a very large polarization, and dielectric constant near Tc is approximately 5000. If you look at potassium dihydrogen phosphate, here this has very low temperature, minus 150 degree centigrade, polarization is approximately 4.7, and dielectric constant is very anisotropic, 10 to the power 5 along C axis and 70 along A axis. So, extremely anisotropic. So, measurements were made on single crystals. If you look at perovskites like barium titanate or lead titanate or potassium niobate, in this case barium titanate undergoes 3 transitions, 120 is the final transition. There are 2 transitions at 5 and minus 90 degree centigrade, but these are the transitions which represent change in the crystal structure, but the material still remains non-centrosymmetric and it still remains ferroelectric, and this has polarization of about 26, and the dielectric constant near the Tc is roughly 160. This depends upon the crystal quality and whether it is in single crystal state or polycrystalline state. So, this is in case of lead titanate, this is 490 degree centigrade, not 450. Polarization again is pretty large, more than 50 microcoulomb per centimeter square, and dielectric constant is large essentially. And again potassium niobate shows 3 transitions, 415, 225 and minus 10 degree centigrade. This has about 30 microcoulomb per centimeter square polarization, and dielectric constants can be very large. it could be anywhere between 900 to 4000 depending upon the whether you have single crystal or polycrystal, etc. So, you can see that near the Tc the dielectric constant is very high. This is what we assumed in previous analysis, which is the field theory, or we call it local field theory of the ferroelectrics. And temperatures better than room temperature of course are desirable, because then the material would be ferroelectric at room temperature and up to the Tc. Materials like H2PO4 is not very useful, simply because its Tc is extremely low and it does not really help us from any application point of view. So, what we will do is that we will put a stop here. In the next class, we will start discussing about the energetics of ferroelectric material, what happens at the transition, because this transition temperature is extremely important. Not only the material goes from ferroelectric to non-ferroelectric state, it is also associated with the phase transition. So, we need to understand what is the nature of that phase transition, and that is very essential in order to understand the ferroelectrics well, and so on and so forth.